So welcome to video 5 in ST4, our course on linear models. And now we're going to look at linear regression and how we can look at the residuals associated with that, which are the leftovers from linear regression. So in simple terms, if we're trying to estimate weight here based on height, here we're inferring for each of these points a best fit. So we have a point here and we have the line down here. So if we drop a line straight down from that point to our red line of best fit, that's our estimate of the residuals or the errors associated with that model. And same for this point here, that's our error. And here down, that's an attempt at a vertical line. Same for this one, and same for this one. Remember, that's because we were trying to regress these values here, x, that's a bad x based on y. If it was y based on x, we'd be looking at a line best fit was like that. Obviously, it would be differently shaped differently. We'd be looking at a horizontal line instead. So again, for these models, we're looking at y is equal to bx plus a, but it could be a different formula where we have some sort of general mean, or maybe different values for our intercept and slope. So all these slopes are essentially the same, and same for the intercept. Sometimes they're denoted as the error, and there might be some sort of mean value if depending on the setup of our model. We also assume that the errors are normally distributed with a mean of 0 and a predictable variance, and that can be inferred from a gamma distribution. So we're looking at the line of best fit, and that's based on a particular model for x, where we're inferring y. So if we're inferring some sort of model where x is equal to y by a new beta 1 here plus some other intercept c, the line of best fit might be positive here, but it wouldn't be the same. It would be some sort of different line, perhaps going like that instead. So you can see here there is the fitted values shown by the black circles, and the residuals correspond to the distances in the green lines. So what we can do with those residuals to estimate the error in our model is sum them up, get the sum squares of the residuals, and that gives an estimate of the extent to which our model is good or not. So that means when we're looking at, we're assuming some sort of linear model, these should be independent of the response of the predictor. So the errors should not be correlated with x or nor y. So they should be constant. So we plot the fitted values against the residuals. You should see something like this where there's no real trend. So if you think about it, in a sense, you're taking away y from the residuals so that there should be no correlation when you plot them like this, which you can kind of see if you think about the black points on their own without the green lines. So our difference between the fitted values here, y hat, the observed values, that error, the absolute value of that error is the residuals. It's not there in the sense of the mistake, it's the variance in the prediction, the estimate of y that is not explained by x. So it could be explained by some other factor. So you might have light as an explanation for the rate of plant growth, but maybe temperature also matters. And when that's not, if temperature is not in our model, there'll be an error that affects plant growth, but we don't observe it, so it's hard to interpret. So you can see that there, we have that distance there, this residual here, and we get the sum of squares of these errors by adding them all up. So you get the error 1 squared, and do that for all, we get the sum across the different errors. You can see that for a different plot here, where we're looking at the best fitted line between the different points. I mean, the residuals E1, E2, E3, E4, E5 are something, we get the sum of squares of them. So that's, we get the SSRes, SSE. SSE stands for errors, SSRes stands for sum as well as squares of the residuals. And you see that we're summing up the difference between y, the observed value, and I'm underlining here the fitted values. And you see that here in another illustration where we have the different values, different points, and we have the residuals being calculated, even if they're very small or big. Those are all errors in our estimate. We can do this with R, where we're able to take our linear model and get the summary from that. We can get the residuals, which correspond to the deviation of each value away from the line of best fit. So here we have different values. So you see this is small at 2.4 for this value here. That's bigger at 6.9. our third value here is 17. This one here is about 6.4, and this is about 6.1. And that means when we're trying to interpret the line of best fit here, the estimate is 11.2. The standard error is 6.6, which is large. And that gives us an estimate of how good our model is. And these points are computed literally from the observed values 33, 67, and so on, to the expected values 35.4, which gives us 2.4 here at the top, 67 versus 60.1, which if you look over here on our right-hand side, we got 67 and our estimate is 60.1. We get 6.9 left over that from that value. And then another one is 34 is our observed value down here. And our expected value is 51.1, which is up here. So you can see those there. So you can talk about the effect of the height and the intercept on the weight. You can see that the height may have an effect on the weight, but with a sample size of 5, we have insufficient resolution to really know if it has a strong effect because the standard error is very large. Same with the intercept. The intercept may be significant to indicate that there's other factors affecting our model, but we don't have information here in the sample set of 5 to really inform further on that. If we had a larger sample size of 50 samples, that's what this is shown here, we can see we still get large residuals. But you see here for the estimate for these values is now larger, and the standard error can be smaller relatively, at least for the intercept, where you see the effect size of the height 50, is still very small. So you can see the multiple R squared, that value is now very, very small, indicating that's actually quite weak. And the diagram for that will look a little bit different to this one. So the adjusted R squared is also mentioned there. So that's a value of minus 0.01 here for this model. So that's R squared modified for the number of models that is present. So if you add additional parameters into your model, such as you've got a model of plant growth based on the height, and then you add in temperature, but if temperature is uninformative, you should not necessarily overfit your model just because you're adding in more parameters. So you get a higher correlation coefficient on its own. The adjusted R square is penalized for these additional parameters, and adjusted R squares may fall if you have additional uninformative parameters. But if you add informative ones, the adjusted R squared will increase, as does the correlation coefficient itself. And that's calculated by this formula here, looking about the variance that's not explained, multiplied by n minus 1 over n minus k minus 1. So that gives us a sense of recovery of k parameters in our model. Finally, just since it's mentioned in this diagram, we also have the F statistic down here at the bottom, and that's the test hypothesis that the regression efficient equals 0. So in this example, actually, it's quite close to 0, which you can see from the R squared value, F is 0.3, indicating that there is no clear effect of heights on this output. So what we'll learn to do later is run this with R code and try different things to better understand how this works.